So this is, we're in 2.3 part 2. And we'll talk about the rational root test. So just to recap what we talked about last week at this point. So we have a polynomial. f of x is a polynomial. I'm not going to write it all out. If f of x is divided by x minus k, some number k, then the remainder, I'll write it that way, the remainder is f of k. That's what we just talked about on the problem that we just worked on. Divide by x minus k, this polynomial, the remainder is f of k. The important thing, the key, what we're going to talk about really for the rest of the chapter, if the remainder is 0, what do we know about k?
We divided by a factor.
You divide it by a factor. If the remainder is 0, then x minus k is a factor. That's our key. That's really the key of this part of the chapter. So x minus k is a factor. What else does that tell us? Factor, when this quantity is a factor, what else do we know? We talked about several things that are equivalent. What do we know about f of k?
0.
F of k equals 0. So f of k equals 0. What do we call the number that we plug into a polynomial that gives us 0? K is a solution. It's a solution to the equation f of x equals 0. We have to have a solution to an equation. What else do we call k when we plug it into a function we get 0? What's another name for a solution? Talked about factor what? Okay, it has to do, k is an x-intercept. That was another equivalent thing that we said. When we have a factor, when we have a solution, and there was one other word that we use right up here. It's a root. So x minus k is a factor, k is a solution to f of x equals 0, f of k is 0, k is an x-intercept of the graph of f of x, and k is a root of f of x. All of those mean the same thing. So that 0 remainder is really the key. And that's kind of a recap of the first part of section 2.3. Those are the things that we talked about. So let's go on to the rational root theorem, or the rational root test. Because what we want is a way to, if we have some polynomial function and we're just trying to figure out what a root is, there are lots of possibilities that can give us 0 when we plug it into the function. We want a way of narrowing those possibilities down. That's what the rational root test does for us. So again, f of x is a polynomial. So we're saying f of x, and I'm going to write out the kind of the general general form of our polynomial. A to the n, a sub n, x to the n, plus, and we talked about this at the very beginning, plus, and we have all these terms, plus a sub 1x, plus a sub 0. So we have all these terms for our polynomial. All the powers on x. And for the rational root test, we're saying that a sub 0, this number that's sitting out here, is not equal to 0. So we need a number out there. I'm going to label these, I'm going to call this P and this Q. The possible rational roots. Of f are plus or minus factors of p divided by factors of q. Before we go into more detail, let's remember we're using several words here. Make sure we understand what they mean. What is, when we're talking about, we know what a root is. A root is, we plug that number in, we get 0 when we plug it in the function. What are we talking about rational when we say it's a rational root? What's that? It's a real number, a rational number. Okay, so we're on the right track. A rational number is a real number, but it's a special kind of real number. What's that? Doesn't have to be positives, because we have positives and negatives here. So when we're talking about a number, we're talking about some kind of number. So when we talk about a rational number, what kind of number are we talking about? Go ahead. Okay, we can write it as a fraction. And we have to be a little more restrictive. So, for example, could I write pi over the square root of 2? Would that be a rational number? No, because both pi and square root of 2 are irrational. So we know, so we're narrowing it down. It has to be a fraction. What do we have to make the fraction out of? Well, pi and square root of 2 are real.
Rational.
So we don't want to use rational to define rational. So we're closer with whole numbers. So we're making a ratio, but we said we can have negative numbers also. If we have whole numbers and negative numbers, what kind of numbers are we talking about? What is it? Integers. Okay, so rational root test is a fraction made of integers. So the rational root test finds solutions that are fractions of integers. Those are the only kinds of solutions the rational root test gives us. There could be other roots to our function. The polynomial could have other roots. The rational root test tells us about rational roots. We're looking for fractions of integers. And when we say factors of p, what do we mean by a factor of a number? All the numbers you can multiply, and what did you say? Together to get the number. So things that, the way I think of it is things that divide evenly into the number. So we're talking about factors of p and factors of q. We make a fraction of those, and we have a plus and a minus for those. So this limits the number of possible rational roots. All right, so let's look at an example of using the rational root test, and we'll see why it's a very powerful thing. So we want to find the zeros of x cubed minus 7x minus 6 equals 0. So we want to find the solutions of this, find the zeros. That was another word we could have used on the other pages, a zero. Well, because of this x to the third, I don't really know how to factor this. But we want to find x, the values of x that we can plug in there and get 0. So we're going to use the rational root test. So we can label this one P, and the number in front here Q. And if it helps you, you can list them out. So what are the factors of P? 1, 2, 3, 6. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. The numbers that divide into 6 evenly. Or negative 6 is what we're looking at. And then Q. We're always thankful when Q is 1, because what are the factors of Q? Just plus or minus 1. So now we've gone from having all kinds of possibilities that could be zeros of this function to 12. 12 possibilities of rational roots. When we're solving these kinds of problems, plus or minus 1 can usually be an easy one to test. If that's a possible rational root, that's an easy one to test just by plugging in rather than doing synthetic division. So let's plug in f of 1. So I just get a 1 minus 7 is negative 6. Minus 6 is negative 12. So 1 is not a 0. So let's try negative 1. Those are easy ones. To evaluate a polynomial, when I plug in a negative, I just change the signs on the odd powers. So I get a negative 1 plus 7, which is 6 minus 6, so I get a 0. So f of negative 1 is a 0. So if I do synthetic division with negative 1, what should my remainder be? 0. And when I do synthetic division, I'm starting with a cubic. What do I end up with after I do the division and I have a 0 remainder? A quadratic. And what can we do to solve quadratics? Factor, quadratic formula. We have all these tools to solve quadratics. So ultimately in these kinds of problems, our goal is to do synthetic division with our possible rational roots until we reduce our equation to a quadratic, and then we can factor or use a quadratic formula, and then we can find all of the roots. All right, so let's do our synthetic division. I'm going to set it up. Negative 1 goes outside, and inside, what am I going to put? 1, 0, 7, negative, and negative 6. We'll do our synthetic division. And we know we should get a 0 remainder, so if we don't, we know we made a mistake. Did I make a mistake already? Yep, this should be negative. That should be positive. There we go. So now what I'm left with is x squared minus x minus 6. My remainder is 0. So what do I do with this one? How do I find the roots of this one? Factor it? How does this factor? X plus 2, x minus 3. That look good to everyone? So this tells me that x equals negative 2, x equals 3, and we already decided that x equals negative 1. are zeros of this polynomial. Questions on that example? All right, let's start. What if we had started, rather than with a cubic, with a fourth degree polynomial? Then when I did synthetic division, I got the zero remainder, I'd be left with a cubic. What do I do from there? How would I go about continuing the problem if the problem asks us to find all the real zeros? What's that? If we know how to factor a cubic, we could factor the cubic. But we have this nice procedure that we started. So what was another idea? Redo what we just did with one of the other possible zeros. If we find a zero of the first polynomial, and we eliminate that, we know one of those is a zero. What if we're left with, these are the possible zeros of that polynomial also. Because when we write this as parentheses, if I write this completely factored out, this would be f of x equals x plus 2 times x minus 3 times x plus 1. Whatever, if one of these makes the original zero, it makes one of these parentheses zero. So it's going to be a factor of whatever's left when I do my synthetic division. So I have all these possible zeros. I can just repeat the process. If we have a 6th degree polynomial, we just keep repeating it until we finally get down to a quadratic, and then we can factor if we can, or use the quadratic formula. So with this procedure, I can just keep doing this process until I find, hopefully, all of the zeros of our function. And we're always happy when we have a small number here, because then our list of factors isn't very big, and we have a small number here because then our list of factors here isn't very big. Now, when you do this, when you do these problems on a quiz or a test, we're not going to make you search through a huge list of P's and Q's to find your factors. Either we'll set up the problem so it's one of the earlier ones, or we will give you one. We would say, given that x equals 2 is a zero of this equation, find the rest of the zeros. So then you know where to start. You have somewhere to start. All right, so questions on that example? So let's look at, I want to look at one other example where we do have where we do start with a fourth degree polynomial. So let me find the example I wanted to do. There we go. So let's look at this one. We want to find the zeros of x to the fourth minus 3x to the third plus x minus 3. We're going to find the zeros of this polynomial. I'm not sure how to factor this because of this x to the fourth and x to the third. So we're going to go to our p's and q's. So this is p, this is q, and I'm happy already because p is prime and q is 1. So for the factors of p are nice and easy. What are our factors of p? Plus or minus 1 and plus or minus 3. And the factors of q are just plus or minus 1. So our list is very small here. So we can substitute in plus and minus 1 to find to see if those work. Those give us if f of 1 or f of negative 1 is 0. So let's find f of 1. F of 1, I get 1 minus 3 is negative 2 plus 1 is negative 1 minus 3 is negative 4. F of 1 is negative 4, so that doesn't work. F of minus 1 is an easy one to test also. So I get 1 plus 3 is 4, minus 1 is 3, minus 3 is 0. So negative 1 is a 0. So that's where we start with our synthetic division. I'm going to put a negative 1 here. And how do I want to set this up? Get a 1 for the x to the 4th, minus 3 for the x to the 3rd. What else do I need to put in here? A 0 for the x squared, 1 for the x, and a negative 3. We know we have to get a 0 remainder here, so if we make a mistake, we can go back and check ourselves. So we get a negative 1 here, so there's our first synthetic division. So we're left with x to the x cubed minus 4x squared plus 4x minus 3. And our list here, we already eliminated plus or minus 1. Yes? Were you just stretching? Okay, no worries. So we already eliminated plus or minus 1. So let's try our synthetic division with x equals 3. So I'm just going to go here. We've already picked out our possibilities, so we'll try this one. So we get a negative 1. And I didn't need the 0 here. And a 0. So now we're left with, that turns out to be a root. So we have, for this one we have x equals negative 1 as a root. For this one we're left with x squared minus x plus 1. And we know that x equals 3 is a root. Well, now I'm down to a quadratic. What can I do with a quadratic? Factor, quadratic formula. Does this factor? Does not factor. So we can use a quadratic formula. We can always use a quadratic formula. Turns out that this doesn't have any real zeros. We get complex numbers when we put this in the quadratic formula. So we could use a quadratic formula, find our imaginary zeros, our complex zeros, and we'll talk about those coming up. So our real zeros would be x equals minus 1 and x equals 3. If we put this in the quadratic formula, our coefficients here, we would see that we end up with complex zeros. But the process was test our factors of p and factors of q. With synthetic division, we're looking for the 0 remainder. The 0 remainder is our key. Questions on that example? All right, last thing we need to talk about is Descartes' rule of signs. But I have one quick question for you before we do. What if our problem asks us to find the zeros of this? We're finding the zeros. When we used our rational root test, we said that we needed a constant out here to use our rational root test. If we use a 0, then that tells us we don't get very much information. What can I do with this polynomial? I can factor out an x. This equals x times x to the 3rd plus 3x plus 1. So immediately, what is one of the zeros? X equals 0. And then I can use the rational root test on this part inside. So if you have an x or an x squared, something that's common to each term, you can start by factoring. You don't immediately have to jump to the rational root test. You can factor first. You can use the tools that you already have first. All right. Descartes' rule of signs. Another way to limit what possible things we do synthetic division with. Descartes, very famous mathematician. He's the person that Cartesian coordinates are named after. Descartes' rule of signs tells us we have a polynomial, f of x, it's a polynomial again, and our constant term, that number, is not 0. So we have some number at the end of our polynomial. Descartes' rule of signs has two parts. The number of positive real zeros So Descartes' rule of signs doesn't just tell us about rational zeros, it tells us about real zeros. The number of positive real zeros is equal to the number of sign changes, and we'll talk about what that means. In f of x, or it's less by an even integer. Even it was just a multiple of 2. So it's less by 2, less by 4, less by 6. And we'll talk about the sign changes, what we mean by sign changes, in just a second. The second part, the number of negative real zeros. And again, Descartes' rule of signs is telling us about real zeros, not just rational zeros, is equal to the number of sign changes in f of minus x. Or less by an even integer. So Descartes' rule of signs doesn't tell us what the real zeros are, it just tells us how many there might be. But that can help us eliminate some of the factors of p over the factors of q that we test. So let's look at an example. Finding the sign changes is really easy. So f of x, we'll say is 3x to the third minus 2x squared plus 5x minus 1. So the sign changes, we're just talking about the signs in front of the coefficients. So here it's positive, and it changes to negative. So there's one sign change. Here it's negative, changes back to positive. So that's one sign change. Positive, back to negative. So that's one sign change. So we have three sign changes. So Descartes' rule of signs tells us that there are three, or we're going down by an even integer. So we're going down by a multiple of 2. We subtract 2, 3, or 1. Positive real zeros. So we either have 1 or 3 positive real zeros. Now let's find f of minus x. To find f of minus x, the sign change for f of minus x, we're just changing the sign on the odd exponents, because negative 1 to the third is negative 1. Negative 1 to the fifth is negative 1. So we're changing the signs on the odd exponents. Negative 1 squared is positive 1, so the sign doesn't change. So we change the sign on the negative exponents. Minus 3x to the third, minus 2x squared, minus 5x, minus 1. So we're just changing signs on the odd power terms. Negative, 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 so no sign changes. So Descartes' rule of signs tells us that there are no negative real zeros. So if we were looking at our p's and q's for this polynomial, and we looked at Descartes' rule of signs tells us throw out all the negative ones. There's no negative real zeros for this polynomial. So we're only looking at the positive ones. So if we started out with a list of 12, Descartes' rule of signs would cut that down to a list of 6. So it cuts our list in half. If Descartes' rule of signs, for example, tells us that the polynomial can only have one positive real zero, and we find it, then we know the rest of them have to be negative or imaginary. So we don't even look at the other positive numbers. If we find one of them, we just quit looking for the other positive ones if there can only be one. So Descartes' rule of signs can really help us narrow down our search when we're looking for roots of our polynomial. So that's what Descartes' rule of signs tells us. Questions on that? All right. Let me give you our homework, but before I do the numbers, pretty short because I cut the other assignment down. Some of the problems ask you to list the possible rational zeros of the function. When it just says list the possible zeros, it's just asking you to find the factors of p over the factors of q. It's not asking you to find the zeros, it just says find the possible zeros. So make sure you pay attention. Some of the people in the other class were trying to find all the zeros. Some of the questions just ask you to find the possible real zeros. And that just means list the factors of p divided by the factors of q. All right. Homework. There you go.